All right, so today's study group will be on decision trees. And before we get started, wanted to address a question we got from Melody about confusion matrices showing different results. And this is in the building trees using scikit-learn lab. And over here, they show another couple of ways of doing confusion matrices. And first off, they have this crosstab method, which I believe just uses pandas, and oh, I guess it does it for you here. Yep. And so basically the question is, these numbers are different, and that's just because they're using different inputs. So for this example, they're using the test set, and I believe y-pred should come from the dot predict on the test set. And then in this plot confusion matrix, they're throwing in all your data. Not very common to do this, I will say. I'm guessing they just wanted to show a different way to do it. But typically, you would have separately a confusion matrix for your training data and your testing data when it's run through the model. So yeah, something that I wanted to point out as well, that usually confusion matrices, good to see one for your train set, one for your test set. One that also helps you check for overfitting if you have, like, for example, in these false positive and false negative squares, if you have zeros in your train set, that's great. But in your test set, if you have much higher numbers, it's a sign of overfitting. So that's one thing to look out for.
So the inputs on that matrix then, where it's X and Y,
Mm-hmm.
is that Y supposed to be the predictions then? I mean, that's how it's...
Yeah, so that's also somewhat confusing. I know that there is, from scikit-learn metrics, there is plot confusion matrix and there is just confusion matrix. And just confusion matrix will give you it in like a little array without this like heat map. So the way that plot confusion matrix works is you feed it in the classifier and you feed it in your test data. So you feed it in your like X train, Y train, or your X test, Y test. And what it's doing is actually doing the dot predict within this method. So within plot confusion matrix, it does the dot predict on whatever X you're giving it, compares that to your Y, to your actual values of Y, which I know is different from the regular confusion matrix function. That one, I believe, takes in, similar to this, I believe that one does take in like your Y predictions and your Y actual values and just compares those. So yeah.
So that would make sense then why, when I ran it and put in my Y predictions instead of Y, I got a perfect matrix.
Yes. Yeah,
yes.
That's right. Yep.
Yeah.
Yeah, they both work. I don't know why they decided on different inputs. Most of the scikit-learn metrics actually take in actual Y and predicted Y. So I don't know why this one does it. I don't know why this one embeds the dot predict function there. But yeah, that's how it's set up, which is inconsistent, but at least we have this nice diagram here that we don't have to like seaborn. I know that for some of you who have the older version of scikit-learn and like don't want to go through the process of updating it, if you just Google plot confusion matrix on Stack Overflow, I know that a few people have provided like the hard coding for seaborn on just like creating this from the confusion matrix output, just in case you don't want to deal with like upgrading your scikit-learn in your learn environment. But cool. Before I get into decision trees, any other questions? Cool. Well, let's get started. Decision trees are very exciting. They're one of my favorite algorithms as well. And I'm actually going to be talking about decision trees in the context of both regression and classification, just because I think, at least for me, it made more sense to look at regression first, just in the way the cost function works. So maybe that will be helpful as well. And then I'll expand it to how it works for classification. So to start, we're going to figure out what decision trees are, talk about a little bit of terminology. We're going to go into, actually, I flipped the order, but I didn't update this agenda. But we're going to actually start with regression trees and then go into classification trees. I also have a notebook with implementation of all of that, so I'll go through those. And then lastly, the pros and cons of cart trees. So CART trees actually stands for classification and regression trees. So CART trees should not be written as CART trees, I'm realizing right now. All right, so what are decision trees? This flow chart might look, this like structure of a flow chart might look very familiar, and that's literally what a decision tree is. Given a test data set or a test point, all you have to do is traverse down the tree to figure out what your classification is. So in this case, you'll just have like a yes, no target for this. What is your reply to this party invitation? And the features would be there, are there any girls at this party? And will Miley join the party? And then your targets will be you go or won't go. And so all you have to do is with your test data, traverse it down the tree based on these features, and then that's how you arrive at your prediction. And we'll go through more concrete examples after this, but pretty much a tree is a flowchart. Some terminology, each of these where you split your data or have different conditions, each of those are called nodes. The very first node is called a root node, and any other node after it is a child node. And then any final value would be your terminal node. Any like final points where you end up, those are your terminal nodes. To go along with the tree terminology, each split is a branch. And yeah, at each node you split your data. So they're actually known as splits and branches. I think that's all the terminology. Yeah, any questions about this here? Cool. So,
excuse me.
Mm-hmm.
Our labels on our target variables are now go and won't go.
That's right. That's right.
So this would be the base of our logarithm.
This will be like ones or zeros. If that makes sense. So in this case, you could say like go as 1, won't go as 0, and you're just going to predict ones or zeros.
I just want to know, this is where we decide to max features of our class or not?
Yeah. So max features, that's something that I'll talk about in a little bit.
Okay, thank you.
Yeah, you're welcome.
Wait, what's the context of this decision tree?
Yeah, so this data frame, I know this is not, I guess I should have used a better example, but with this, you can imagine your data frame looking like you have your target column being go or won't go. Mm-hmm. And your features will be, are there any girls, and will Miley join the party?
Miley Cyrus?
I have no idea.
Okay.
This is an image I took from, I think the labs used this exact image, if not like the old lab did. But yeah, but it's the idea. Yeah.
Curious.
Yeah. Anyways, the idea of a decision tree, you sort of think of it as segmenting or partitioning your feature space, and that's how you determine your conditions and splitting. All right. Yeah. Any other questions about like terminology? Yeah. This context, I swear I didn't come up with this myself. All right, so we're gonna start with regression trees that work very similarly. You actually also traverse down a tree, but you end up with a continuous output, and I'll sort of talk about how that works. So here I just have a scatter plot of our data set. So this is a 2-feature data set. The 2 features are hits and years, and this is for professional baseball players. So on the x-axis, you have the number of years someone has played in professional baseball, and on the y-axis, you have the number of hits they've made over their career. And the target variable in this case is going to be represented by the color of the points. And so not super clear, but here you have purple being lower salaries and red being high salaries. And salary is eventually what we want to predict. So you can sort of see like an overall pattern going on here. On the lower end for lower salaries, you typically have fewer years of experience. You can sort of see like from left to right, it's going overall like purple to red, and same from bottom up. With fewer hits, you have lower salary. As you get more hits in your career, you tend to go higher. So for example, this like very red point is high number of hits, a fairly high number of years of experience. So this is what our data set is. So the idea of a decision tree is you're gonna find out how to split this data set into different parts and segment this data set so that you end up with conditions that make sense that you can traverse down your tree with. Questions about the context? All right, I'm getting distracted by the chat as well, but no worries. Okay, so the way decision trees work is it's gonna actually create these splits. Now, as it's creating these splits, some conditions you look out for is these spaces or these subsections are all distinct and they don't overlap. And then the values of your prediction will be the mean value of each region. So basically with these splits, this is the tree that results. So for all your baseball players, it determined that, all right, the first split you're gonna make is your years of experience. Is it under or above 4.5 years? So if you have a test data point, the first thing you're gonna do is see whether you have less than 4.5 years or above 4.5 years. And because here we already arrive at one terminal node, if a baseball player has less than 4.5 years, we're going to come up with the estimate or the prediction of 225,000. And that's basically like the average of all of these points in this section. Now, if a player has more than 4.5 years of experience, based on how this tree decided to split, we also have to look at whether it has more than or less than 117.5 hits. And if it's less than, it'll be in this R2 terminal node, which has an average of 464,000 as salary. And if it's above 117.5, you arrive at an average of 949,000 as a salary. So questions about this so far? The next slide, I'm going to be talking about how you determine the best splits. Cool. So with this, let me just move my windows. All right. So the cost function.
Sorry, I had a question on that.
Yeah.
Sorry to
No
interrupt.
worries.
I was a little late.
All good.
In that previous decision tree where you had less than or over 4.5, is there anything resulting from exactly 4.5 in that case?
I guess not. I guess to be more specific, you would have like a less than or equal to, or more than or equal to, depending on, yeah, there should be like, for exactly 4.5 in this exact tree, I'm not sure what it would do, but it would probably be in, either one. Cool.
Thank you.
You're welcome. All right, so how do we decide on the best splits? So the cost function is actually something that's very familiar to us, mean squared error. So the mean squared error here and how they decide on the best split is where the mean squared error is the lowest. So mean squared error here is measured for each point, and let's take a look at like this first 4.5 line split. What they're gonna do is they are actually measuring the distance between let me use a different annotator. So let's say your mean salary ends up being here. What you're gonna do is with the split, each section has a mean salary. So actually that's not correct. Let me use a different. So with R1, let's say the mean salary is about here, or your mean salary is about here and actually more like here. So let's just imagine the first split is the only one that's been done. All you're doing is within each split, you're measuring the difference between each point and the mean salary. That makes sense. So again, let's say like about these points have a range of between 100,000 and like 400,000 compared to the mean, and the mean in this region was 225. You're going to take the mean squared error of that. On this end, a combination of R2 and R3, take a combination of all the mean squared errors between each individual point and the average. And wherever the overall mean squared error across, and you're summing up both mean squared errors across both sides of the split, wherever that's the lowest is your best split. Does that make sense? Cool. I am seeing the chat. If you could have a decision tree where terminal nodes are different linear regression models, that's actually very interesting. That is actually a way to use model stacking, which is very cool. So with something like model stacking, what you could do is maybe use a decision tree and you can partition, and let's just go with the example of the housing prices that you're dealing with. One thing you could do is you could build a decision tree with like maybe a depth of 2 to maybe like partition your features, partition your data into 4 different parts, and maybe you build a regression model for each of them. And because of that, each subset will be more contained. Like you won't have as many outliers within them. You could build more precise linear regression models for each part, which is very similar to what some of you did by like, I think some of you had a focus of like the lower price homes or like the luxury homes, quite similar to that as well.
And the benefit of that is your prediction would be on a continuum rather than just the mean of that partition.
Yes, yes, that's right. So typically with regression trees, you're actually going to make many, many more splits so that you end up with more precise predictions. Because currently where this stands, you have only 3 possible prediction outputs, which doesn't really make sense in a regression. But the idea is you're going to keep doing this process over and over again, like possibly, I don't know, splitting this further, maybe like this and like this. Again, remember these splits cannot overlap. And it's just going to keep doing that until you reach like enough precision. And that's actually something that you do tune in a regression. How deep does your tree go? And that you would actually tune to check for overfitting and underfitting. Because you imagine if you have a lot of splits, you tend to overfit, and with fewer splits, you underfit. But cool. So these math equations, this one basically is the first. Let me like just circle this. This first part is just looking at the mean squared error between the average and each data point. And then this is just doing it across the 2 sides. And these bottom equations are really just a breakdown of these. One more thing I wanted to mention, the approach is top down and greedy. So two concepts coming into play here. Top down, meaning that you're going from big to small. You can only further split regions that have been split. So basically, let me undo this. Out of here, I can only further split R1 within itself, R2 and R3 within themselves. So I cannot create another split that looks like this. That is not a possible split. I can only make splits within each region. So that's top down. Each region gets smaller and smaller. Next, greedy. What it means by it being greedy is that it's going to decide what the best split is at only that particular moment in time. So perhaps, yeah, these 2 splits are the best splits now, but maybe if you were to change the order of the splits, you might get a better result. For example, instead of those splits, maybe if I actually first split this and then split the years like this, which is a different tree, maybe this gives better results. But because it looks for the best split at each step, it is a greedy approach, which is another thing that does sometimes lead to overfitting. Cool. All right, any questions about this? This is pretty much the algorithm and like how the gradient descent works. The gradient descent works by like adjusting where the split is. And basically at each, to figure out each split, it checks all the values across every feature to figure out what the best split is. And it does this via gradient descent. So it doesn't check every value, but it optimizes for those values. Cool. I'm actually going to go to the notebook after this slide. Let's take a look at how regression trees work in practice. So here, what I'm using is the same data. I'm going to use this header CSV that I also uploaded to your study group repo. And this file is not here. Give me a second. I think I have it in a resources folder. All right. So don't forget to change this. All right. So here we have our hits, our hitter CSV that has all of these columns. But for now, let's just use hits and years to predict salary. So with that, this is what our data set looks like. I'm going to define my X and Y, do my train test split real quick, and then I'm going to instantiate a regression tree. So a regression tree, let's pull up the documentation. Wait, I think I have it linked here. Regressor, here we go. So with decision tree regressor, again, you have a lot of hyperparameters. There's an entire lab dedicated to the different hyperparameters of trees. And right now, we're just going to deal with the max depth. So the max depth, as I mentioned, is something that you can tune to determine how many steps your tree can, how many splits your tree can make from the root node. So we're just going to start with a max depth of 5 for now, and then same syntax that we've been doing before. We're just going to fit it to our chain set. So something that's pretty cool, and I hope this works because it doesn't always work in my learn environment. But here, there we go. So with a max depth of 5, what that means is it can only go 5 levels deep. So you can see 1, 2, 3, 4, 5. And this is our tree visualized, which is pretty cool because if you zoom in, and hopefully it lets us zoom in, I guess not too much, but you can sort of see what the mean squared error is at each node. So each node, it tells you the mean squared error, how many samples are in each node, and the average value at each node. So all you have to do is with any data point, here you can see, I wish I could zoom in a little more. Let's see how far this goes. Yeah, this is not working. But definitely do it on your own. Let me see if maybe doing this will help. Never mind. But anyways, with this, with any data point, and in this case, it does say x0 and x1. I believe in this case, x0 is going to be hits and x1 is going to be years. So with any value, all you have to do is see, all right, is it above or below 4.5? Years, is that above or below 4.5? If it's yes, if it's no, and just keep traversing down the tree. And each of these conditions will be something on either x0 or x1. If I had more features, it could be any of the features. So yes, thanks, Tim. That's a really, really good point. If I just reduce the depth, you'll have a clearer tree. So let's just do that real quick. Yeah, that was a good idea. Thank you for that. Yeah, so you can see here, you start off with your division of whether it's greater or smaller than 4.5 years of experience, true, false, and then your next bit on the true side, it actually says, all right, well, let's look and see if you have more or less than 3.5 years of experience. So you're just going to keep partitioning your data set, and your data points, any test data point will fall into one of these 4 terminal nodes. And wherever it falls, these will be their predicted values. So you can imagine as your tree gets deeper, you have a wider range, not a wider range, but you have more precision in your predicted values because you'll have more values that you can end up with. And yeah, you can sort of see that the number of samples in each split end up at 51, 19, 73, 67. And yeah. So with that, you can actually also make predictions. And then we can take a look at our RMSE. Our RMSE is actually only $380 off. And this is with, wow, is this really with like a max depth of 2? That's actually really impressive. But yeah, this is also a small data set. So one hyperparameter to tune, as I mentioned, is your max depth. So one way to tune this hyperparameter, because max depth is one that really heavily affects whether your model over or under fits, is to just grow your tree very deep and then prune it back to a subtree. All that means is, because it's a greedy algorithm, if I have a tree depth of 5 versus a tree depth of 2, the first 2 layers are going to be exactly the same. And that's because it's a greedy top-down algorithm. So if I increase the depth, it's going to have this same starting point and then just further split from these. And that's because it's greedy. So what we can do here is we can change our depth range. So here I'm just testing from 1 to 9. I can fit my decision tree regressor with a max depth of this depth in depth range. And then I'm just going to do a quick cross validation with 6-fold cross validation, and let's just see what we get. So with this, you can see our mean squared error is the lowest at 2. And then after that, our mean squared error tends to go up, possibly due to overfitting. Would be cooler to see, let's see, this is doing a cross validation score. It would be cool to see a train versus test mean squared error. Unfortunately, I don't have here. But typically with a train and test mean squared error, what that would look like, and let me just draw like an estimation of what that typically looks like. With your training data, and this first line will be for your training data, you tend to have like an overall decreasing mean squared error as you increase your tree depth, right? You can imagine as you increase your tree depth, you can get more granular with your predictions. Therefore, your predictions will become more accurate. However, you do tend to overfit. So typically what your test MSE looks like, and actually this shape follows, typically what your test MSE will look like, it will get lower to some point, or actually before that, more accurate. It will start probably higher than your trained MSE. It'll get lower to some point, like for example here, and it'll start to overfit. And then your test RMSE or MSE will start to deviate from your trained value. So this is actually a very common shape if you were to compare your train and test errors. So it's always good to look for, this region where your train and test values are very close. And that's just to preserve the predictability or the predictive power of your model. Let's see, I see some questions. Since it's always a yes/no classification, will you always have number of results in the powers of 2? Yes, actually, I think so. Not in the powers of 2 because I would say more likely a multiple of 2 because, for example, after splitting, let's say maybe after this split, maybe this split decides that the best way to split it is a way that ends up with 1 sample here and 50 samples here. This one doesn't, this one is unable to keep splitting, but this can keep going further. So not exactly always a power of 2. Is it best done graphically, or is there a function to tell you the best max steps? Kind of. So actually tomorrow or Tuesday, depending on time, probably Tuesday, unfortunately, I'll talk about something known as grid search. And grid search is actually a pretty neat function that you can give it a range of values and it'll test your model for you. And you're actually able to use grid search to test all the combinations of all your hyperparameters for each model. And with that, you can automatically determine your best max steps with your other features as well. So it'll actually give you the best combination of hyperparameters for each model. That is in topic 30. I know it's somewhere, I think it's somewhere halfway between in topic 30, but I will go through an example of it on either tomorrow or Tuesday, depending on time. But cool. Questions about this so far? There are a bunch of other hyperparameters to tune. Max depth is just usually the one that leads to over or underfitting. So that's usually one of the more straightforward ones to tune. Other ones to tune can also be, I think there's one called min sample split. And min sample split basically tells you, it also helps overfitting because you can say that I have to have a minimum number of like 20 samples before I split further. So if I set my min sample split to be 20, this node here will stop splitting because this node only has 19 samples. And so you stop getting that granularity with that if it traverses down that way. Cool. Questions before I hop back over to classification trees? All right, so just as a recap, why don't we want to make too many splits? Because too many splits will lead to overfitting because your predictions get to be more and more granular. And why a regression tree over multiple linear regression? Multiple linear regression was kind of annoying because you kept having to check for assumptions, right? You had to check to make sure your p-values were okay. Multicollinearity wasn't a big deal. Heteroscedasticity was another thing. So with regression tree, you actually don't have to worry about any of that. With regression trees, you also don't have to worry about scaling at all, which is pretty neat. So you can pretty much take your data set. You barely have to do any cleaning, maybe at the most like creating your categorical variables, but you can pretty much just dump it in your tree and it'll work fine. So regression tree, definitely an alternative to multiple linear regression. You're definitely not going to use it in this upcoming project, but if you do decide to do another regression project in the future, definitely check out regression trees. All right, next, classification trees. So as a super quick recap, the difference between classification and regression is the nature of your output. Classification, your outputs are categories or discrete variables, and regression, you're predicting a continuous variable. So the differences between classification and decision trees, sorry, classification and regression trees, how the best splits are determined, and also, I guess that was a recap question that I put here the last time, but what's the hyperparameter we tune for regression trees? We tune max depth. Cool. So the main difference is how best splits are determined. So this is our trusty iris data set. Here I only took out 2 of the features. So here we're just looking at petal width and length. So these are the only 2 features we're going to consider here. And same concept, you're going to work on splitting your data set. And here, x-axis petal width, y-axis petal length, and the 3 colors represent the 3 different species of your irises. And again, this is what we want to predict. So based on this, I feel like a lot of people can look at this diagram and have some guesses on what the best split will be. I don't know if anyone wants to like make a guess on like where these will split nicely. Anyone? Common answers include most of the time like isolating this one on its side. So a lot of like people will say like, all right, maybe I split it like this first, and then later perhaps like something like this. That's a possible tree. Other options I've heard like maybe something like this and then like this. All possible splits, right? But the idea is how do we determine the best, right? Because previously what we were doing with our regression tree is we were comparing it with the mean. We were comparing each data point with the mean of each region. But here the mean doesn't really make sense because you can't calculate the mean of like these categories. So instead we have a different cost function.
Could you do 2 horizontal splits on this, or is that not allowed?
Yeah, absolutely. You can absolutely do 2 horizontal splits like this and like this, which I believe if we go to the next slide is the actual best split for this. So, oh, I guess not yet. But these are the actual best splits. So actually, let me talk about this slide first. So this is using the Gini cost function. So later on back here, I'll talk about there are 2 main cost functions that we use or choose between for our decision trees, one known as Gini, the other one is entropy. So I'll go through those in a little bit, but yeah, these happen to be our best splits. And as you were saying, Stephen, the first level was actually to look at whether petal length was greater or less than 2.45. And if it was greater, it does the second level split. And you can sort of see here with our first split, you end up with a pure node. And then with our second split, it was pretty good. We have like 36 species 1, and then 1 of species 2, and then 5 and 38 at this split. So overall, pretty decent. And then of course, it will tell you that at this node, you'll predict species 0. This node, you'll predict species 1. This one, you'll predict species 2, just whichever one the majority is. All right, so now back to the cost function. How do you decide on the best split? We have these 2 new cost functions known as Gini or entropy. So instead of using MSE, we're using these new cost functions. And these are the cost functions that you're going to do the gradient descent over. So first, there's Gini parity index that is measured between 0 and 0.5. So this is the equation for that. It is just a sum of the squared proportions. So here you can see, if I want to look at the Gini parity of the phones that people have, let's say in this data set of like 25 people, 10 have iPhones and 15 have Androids. This is the Gini parity, 0.48. If you had a purely everybody has an iPhone situation, your Gini parity index will be 0, because you can imagine this will be 0 out of 25. No, sorry, this will be 25 out of 25. This will be 0 out of 25. That all squared, minus it off. If you have a pure sample or a pure split or a pure section, you would have a Gini parity index of 0. So it's better to have a lower Gini parity index score. So that is just one of the 2 main ones that you can choose from. The other one being entropy, and entropy uses a log formula. There is also a built-in function for entropy, so you don't have to worry too much about that. But also you don't have to calculate entropy, it does it for you. But pretty much entropy is measured between 0 and 1, and you want your number to be, again, as close to 0 as possible. This is just an example of how you would use the entropy function. if you have a split of like 5 and 9 of, I think this is just people playing golf. So 5 out of 14, I think comes up to 0.36, and then 9 out of 14 comes to 0.64. You would find the entropy of that, which is using the negative log formula. And this comes up with an entropy of 0.94. If you had like 0, 1, you would end up with a lower entropy number. So in your hyperparameter tuning, this is actually something you can tune for. I have the documentation over here. Criterion. So the function to measure the quality of the split, the default is the Gini coefficient, but you can also use entropy, and that's something that you use it when you instantiate the model. So the main idea of these two cost functions is you're trying to maximize purity after a split. And so what it's going to do is just going to try different splits and just measure the Gini or the entropy with each split and determine where the best split is. And again, from each terminal node or from each node, it's going to figure out what the best split is across every feature that you have.
Is it better to use Gini or entropy for our data?
Hard to say. Honestly, this is one of the things that you would you would run a model with one of each and then just see which one does better for your data set.
Mm-hmm. And the base of log in the entropy formula is because we have two labels, yes or no?
Ooh, that's a good question. I'm honestly not too sure about that.
For example,
yeah.
if we are categorizing, for example, the colors of a series of clothes, for example, brown, black, and blue. So this
will it be a base of 3, right?
Yeah.
That I'm actually not too sure off the top of my head. I know that there is a lab that talks about that, and that maybe might say, but I don't think so, but I will double check. I don't think so, only because in this general formula, your C is not part of this, if that makes sense, and your 2 isn't changing. So I will double check that and then let you all know. Let me write this down. But yeah, that's a good question. I actually never really thought about that. I do think it is log based too, but I'll double check for you all.
Okay, thank you.
Cool. All right, so any other questions about this? So it turns out that the best splits are in fact both horizontal lines, and that is also possible because after it's done this first split, and this is the first split at 2.45, the next best split just so happens to be here. And you can sort of imagine that, like, in terms of like misclassified or like points that are on the points that end up becoming the minority within each section, here you only have 1 on this side and apparently like 5 on the other side. And if you were to do a vertical line, I don't think you can get that same purity. But cool. From here, we'll just do a quick example in scikit-learn using our trusty iris dataset again, getting this is our scatter plot, do our train test split it with a max depth of 2. Take a look at what our tree is. This is actually the same image that I had on the slide. Our predictions, and we can see our accuracy score is 0.96. What I should have here as well is our plot confusion matrix. So let's see if I remember the code for that. Do I have confusion matrix here? I guess not. So let's do from scikit-learn.metrics import plot confusion matrix. And again, it is C-tree X test iris and Y test iris. Oh, nice, first try. There we go. So yeah, this is what our test data confusion matrix look like. So pretty good, just 1 misclassified point. Again, this is a very, very small data set. So the 1 misclassified lowers your accuracy score down to 0.96. But again, usually you want to check all your other scores as well. Cool. So finally, you can also do a cross-validation to figure out what the best depth range is. Again, different ways to do this. Here, we're using our cross-validated accuracy score for different depths. You can sort of see it sort of, and this might be, yeah. So with a max depth, you can sort of see it plateaus out at a 0.96 after 3. So maybe the best next step is 3. So let's just see what that tree ends up looking like. There you go. So it seems to do a different split here. So after doing this 4.75 split, it does a split on your x2 and then x3. Cool. Does this look different? Never mind. I'm not sure what's going on here. But anyways, yeah. Turns out best one is depths of 3. I'll take a deeper look and see what went on over there. Any questions about this?
So that decision was made using accuracy as your score, but put in different metrics there.
Yeah, you can definitely use, again, like it does depend on your context, right? Like for example, for some cases you might want to look at recall, and in your cross-validation, you can actually tell it what score you want to maximize over, or what score you want it to output here. So that's something that you can do as well. Grid search also has that function.
That seems like it's probably one of the more important decisions we make when we're actually doing our models in like a real world circumstance. So are there like givens for depending on the problem you're trying to answer? Like for example, I saw that for image like recognition and classification that they use a lot of average precision. Yeah, so is it just like depends on the context of your situation, which is better?
Which metric to choose, or are you talking about in terms of, okay, in terms of metric, it does depend on your context. So I think in classification, a pretty common one would be like disease detection. And with disease detection, you always want to maximize your recall score. So disease detection is usually like a binary. So yeah, it would be your recall score, because you want to make sure that you're not telling people that they don't have a disease when they do. And then that is something that you can tell cross-validation to output. And also in your grid search, which I will talk about either tomorrow or Tuesday, grid search is really just like using the code. Is actually the functions are pretty straightforward. So if you want to take a look now, you definitely can. In grid search, you basically give it like all the parameters of all the different hyperparameters you want it to test out. It'll test every combination of them. And then it'll spit out the best combination of parameters based on whatever scoring you tell it to choose from. So grid search will do that. Just one caveat for those of you who are interested in trying grid search before I talk about it, can take very, very long because you are testing every combination of every hyperparameter you're asking it to do. So an example is for your decision tree, you can be like, all right, I want to test all the depth ranges between 1 and 10. I want to test min sample split between like 20 and 100, and so on and so forth. There's a lot that you can tune with decision trees. Maybe you're also doing your Gini and entropy criterion, maybe seeing which one is best. So if you're doing like 2 values for criterion, 5 values for depth, 10 values for sample split, you end up with like 2 times 5 times 10 times your model is going to be training and predicting. So it can take a very, very long time. But yeah, in terms of metrics that you want to optimize for, it is up to you and does depend on context. Cool. So that's good. That is decision trees. Pretty straightforward. The models that we will be talking about tomorrow as well as Tuesday, and I'm actually going to turn ensemble methods, which is our next topic, into 2 different study groups. And then I will actually be combining SVMs and pipelines into 1 study group, which is our last 2 topics for this phase. Questions so far before I get into like the final pros and cons?
Hi, I've got one more question about this graph here actually. I see that the first horizontal line, it is best that it's, say, like halfway between the 2 groups. But I didn't see how Gini says it's there instead of just either as soon as it leaves one group or the other?
Oh, do you mean that like Genie can't optimize whether it's like 2.45 or like it pretty much looks like it can be between like 2.1 and 2.9?
Yeah.
Is that your? Yeah, that I'm actually not too sure about, to be honest. Yeah, I'm honestly not too sure. Perhaps they're looking at like the halfway point between like these points, but I would have to look into that. I'm not sure how it decided that like this would be the best fit, because you're right. Either of those cost functions will not tell you like is 2.45 better or is like 2.5 better, because technically Genie and Entropy will both give you the same criterion result. So yeah, that's a good question. I'll look into it and see if I can find anything about that. But yeah, that's a good one. Anything else? All right, I was just writing that down. Cool. Now, just to finish off, some quick pros and cons of trees. So advantages, the same model pretty much can be used for both classification and regression. If you have a not super deep tree, it can be displayed graphically and also very easily interpretable. It is non-parametric, so you don't have to deal with any like assumptions of your data being fulfilled. So again, it doesn't make any assumptions about the distribution of data, unlike linear regression. So therefore, you don't have to like check for multicollinearity. You don't have to check for normality of residuals, stuff like that. You don't have to scale your features, because again, it's just looking for where you can best split your data. The scale of your features really doesn't matter. And it automatically accounts for interactions in a sense that you are looking at each, what am I trying to say? So this is not the best example, but something like this, these points down here are considering the interaction between years and hits automatically. So in not exactly the same way as you would do if you multiply variables together, but in this way, it does account for that interaction between multiple features. So if a combination of features are above or below a certain result, you end up with a different prediction. Are trees only done two-dimensionally? By dimension, do you mean like number of features? Or like, can it be split into more splits? So it can be done with a bunch of features, but usually it does split one thing into two parts at a time, if that's what you mean by dimension. So yes, 1 versus 1x versus y, or multiple features. So yeah, it can be done with, so hits and years are actually both x's, and you can expand to as many x's as you want. So it will basically, when it's looking for the best split, is going to look for splits in every dimension of columns, in every column that you have. So actually with this iris data set, what I could do is I can actually pull out the entire, let me see, iris.data. Yeah, let's not do that one. But for this hits one, I could actually do the entire data frame. So for example, if I rerun this, I think, and then I reset my X and Y as to df.drop salary, and I have to do axis equals to 1. What we can do is we can train our tree. Oops, what is wrong here? So I guess there's other cleaning you can do, but this would work. I didn't do all this other cleaning, but yes, you would be able to do it on multiple dimensions. Let's take a quick look to see what this is. Okay, well, because there are a bunch of like non-numerical columns, but yes, if I were to, for example, take a bigger subset, so let's instead do df, and let's do hits, let's do years, perhaps, let's see, C hits. I don't know baseball, so I don't know what these mean, but we'll see. And maybe C runs. Hopefully that works. Never mind. And let's drop our NAs. Whatever, I don't want to do this right now. But yes, you can run it on multiple columns. And I believe some of the examples in your decision tree labs will do that for you. And then you'll basically see if you output the graph, you'll see that it'll have different X values as well.
Question for that variable that was non-numerical. Does it matter if you one-hot encode it or if you just changed it to numbers? You know, if you keep it as one variable but set C equal to 0 and N equal to 1 or whatever it is, versus one-hot coding, does that make a difference?
So for example, if I don't know what these mean, but let's say there are 5 different leagues and they all have different numbers, different letters that represent the leagues. If I did like an encoding where I do like 0, 1, 2 and keep it in one column, the way that you don't want to do that because they're not numerically related like that. For this kind of data, if it's like a league where they're actually different categories, you won't want to turn them into their own individual dummy variable columns. Versus something like, I don't know, what's an example? I know for your last project, some of you did dummy variables for the number of bedrooms versus some people kept it as a continuous variable. For something like that, again, you still have to have the assumption that your variable changes with the categories. Does that make sense? So
could it be like a range? Like if you wanted to lump things into a range, that would be okay to do. Okay.
Yeah, that's a good idea. Yeah, that's a good idea. So like with the bedrooms example, so let's say you want to classify your house into like apartment, big house and mansion. I don't know. You would want those to be like separable in like the ranges of bedrooms. And that has to like, majority of your points have to fall within those ranges for it to make sense to classify it as like 0, 1, 2 in one single column versus having them split up into different columns.
But if it's binary, you could just do 0 and 1 and that wouldn't make a difference.
Yes, so in this case, and I think, I just saw Steven had there, if it's just A and N and those are the only ones that exist here, then yes, you can just leave it at 0 and 1.
But so any categorical variable that you have, if it is category like 0, 1, 2, like for example, in the mini project where you had like pay 1, pay 2 or something like that.
Yeah.
You want to one-hot encode those for sure.
Yes, I think so.
Okay.
Yeah. A good way to think about it, I think, would be to sort of, I don't know how easy or hard this would be, but sort of visualize it in this form, right? Like with petal width, let's say that I am not sure whether this should be categorical or continuous, right? Basically what you should see is that if you were to plot this against like your target variable, for example, what you could do, one example of what you could do is just look at your, I think something like this might work, or perhaps even like bar graphs, just to look at the distribution of your target variable within each category. So let's say you had, let's say you wanted to predict if a house was a mansion or a regular house. You would look at the distribution of bedrooms between regular house and mansions. And if that looks very different, then you can keep it as categorical, or if it has like a continuous pattern, you could keep it as continuous. I don't know if I'm confusing more people, but basically for these things, doesn't hurt to try both ways. And if you can put into context why you're treating a variable as such, as long as you can make a decision and explain your decision, that should be okay. All right, we're still talking about pros and cons, I think, right? Yes, so interactions. Disadvantages, because I think I went through all of those already. Disadvantages, it doesn't perform as well compared to state-of-the-art machine learning models. So because although decision trees are used a lot, it's more so that it's used in the form within other algorithms that we're actually going to talk about tomorrow as well as on Tuesday. Those other models, ensemble methods, all are built on top of decision trees and make decision trees work better, but they are all built off of decision trees. The recursive binary splitting, which is, that top-down greedy approach of splitting, makes locally optimal decisions that may not result in globally optimal trees. So as I mentioned, at each step is deciding which the best split is. There might be a different combination that results in an overall better result, but it wouldn't know that. And again, easier to overfit, especially with no max depth. So I think, yeah, that is all I have for decision trees. Any questions to close out?
Can you give us a quick explanation of max features and the documentation of scikit-learn?
Yeah, that one is actually very, very cool. So max features here. So this is a cool feature that actually helps you reduce your overfitting. Typically, you don't talk about this one mainly because most people don't use decision trees by themselves, and this is actually accounted for in some of the ensemble methods I'll talk about tomorrow. But max features basically will choose a random subset of your features to consider your split. So it in some way might not give you your optimal split at that moment, but allows you to explore other possible splits. So what this does here, your max features, let's say your data set has 10 features, or no, let's go with 25 features. Let's go 25 features first. So with 25 features, you can give it a square root. By passing in the square root parameter, it looks for 5 features. So it's just gonna randomly pick 5 features at each split to decide to look for your best split. Yeah, and then again, you can also do like a log of your features. And square root and automatic is the square root, and then default is none, which is considering, yeah. So with the default, it considers all of your features. But yeah, that's a pretty interesting one. But I would say if you're just doing a decision tree by itself, worth looking into. But these will be accounted for in the ensemble methods I talk about tomorrow.
And then random state would just be if you're using max features.
Yes.
Something like that.
Yep. Random state pretty much only comes into play with when you have your max features used. Or I'm not 100% sure if there are other ones that also lead to randomness. I don't think so, but yes, seems like random state will just will just be consistent with the random that is choosing per your tree. Yeah, any other questions to close out? All right, well, overall, trees are great. Trees are pretty important just because they are the base algorithm that is fed into a lot of the other algorithms that are more state of the art, like random forests is pretty much an aggregation of a bunch of different trees. We'll talk about that tomorrow. A bunch of boosting models. Boosting I'll talk about on Tuesday. And yeah, one final thing I wanted to say, and I guess I can go more tomorrow, is I think it's a good idea because we've gotten into 4 different algorithms now, which is we're about halfway through all of our algorithms. Good idea, especially for those of you who have already looked at the mini project, to just take a look at the data sets for the final project. So for the final project, you do have a choice between 4 different provided data sets, or you can choose your own data set. So if you want to explore something that you're actually interested in, you have the option to find your own data set and just let me know, and I can just approve your data set and you can work on your own data set, which will be cool. I think it's a good idea to start thinking about that now rather than later. So yeah, just keep that in mind. I will go more in depth on that tomorrow. But cool, if there's nothing else, going once, going twice, hope everyone goes to happy hour later. But also have a good rest of your day, everyone. I will talk to you all at your one-on-ones or at tomorrow's study group.
Thank you. Bye.
Thank you.
You're welcome. Bye.